In this section, 4.3, Modeling Exponential Data, you will learn how to build a mathematical model or a mathematical function that fits data from an exponential function. Let's start with this example. In this table, I have time in months on the first row, and on the second row, I have a savings balance. So this is like the balance of a savings account. And here our account starts with $2,250 in it, and then each month it goes up by a little bit. Something that we learned about in the last chapter was modeling linear functions. And what you should remember about linear functions is that they change by the same amount for each increase of your variable. Here, that would correspond to an increase in our month. Let's see if this data increases by the same amount each month. So we'll make a new table. In the first row, now I have the change in time, and in the second row, I've written the change in balance. So the first box is the change from 0 to 1 month. And to get the change in the balance, you would subtract 2,283.75 minus 2,250. And once you do that, you would get this number, 33.75. And then you would continue calculating the change from month 1 to 2. So subtract this number from that one to get 34.26. And then finish it off with a change from month 2 to month 3 and subtract this number from that one to get 34.77. So what we notice when we create the second table is that the change from month to month is not constant. So that means we are not looking at data from a linear function. So let's consider the other kind of function that we're learning about in chapter 4, exponential functions. And the most important thing to remember about exponential functions is that they change by constant multiples instead of a constant amount. So what that means is that the new value, if you increase by 1, is equal to your multiplication factor times the old value. And if we rearrange this expression, I'm going to divide through on both sides by the old value. What I get is this new equation. The multiplication factor is actually equal to the new value divided by the old value. And the nice thing about this equation is that it gives us a way to check if data comes from an exponential function by seeing if the multiplication factor is constant multiples, remember. So we could make a third table of data, this one. I'm still looking at change in time in the first row, but instead of looking at just the change in my balance in the second row, what I'm going to look at is the balance ratio. So what that means is I take the new balance from month 1 and divide by the old balance from month 2. And when you do that in your calculator, you'll get this number, 1.015. And I'm going to round everything here to 3 decimal places. And then you would go to the change from month 1 to month 2. So you divide the new balance for the second month by the old balance for month 1. And you get the same ratio, 1.015. So these are the same. Maybe it'll be the same in the next month. And when you do this, when you check it from month 2 to month 3 and divide the third month balance by the second month balance, you do get the same balance ratio, the same multiplication factor. So, what do we have? The balance is changing by constant multiples, and that constant multiple is 1.015. So that means that the balance is actually an exponential function of the time in months. So once we've come to this conclusion, we can start to build our exponential model as a function. So the account balance, should be equal to the initial value times our multiplication factor, and then in the exponent we'll put the number of months. And this is just the basic standard exponential function formula that you learned in section 4.1. Now, with this written out, we can plug in our initial value and our multiplication factor. The initial value, we can read off the account balance data because it's given to us. At month 0, initially, the account balance was $2,250. So that's the number that we'll plug in for the initial value. For the multiplication factor, we go back to our conclusion up here that each time we go up a month, we're multiplying by 1.015. So that's our multiplication factor. And then just plug in these two numbers and pick variable names. Here I've chosen B for balance and T for the number of months. So T for time, B for balance. So to finish this off, let's look at a graph of our data and our exponential model. To wrap up our example, we'll go to Desmos and make a graph of our data, and I've already entered it for us. In the first column, I have the months, and in the second column, I have the account balance, the savings balance, and I've already adjusted the graph to show our points, and they're here in green. One thing that you might notice about these points on our graph is that they do look very close to linear, if you just imagine a straight line connecting them. But we calculated in a table earlier that these aren't actually linear, even if they are very close to it. And now over the top of these points, I want to graph our function, our exponential model for our account balance. And here it is in red. You'll notice that it goes perfectly through all 4 data points. And when we're zoomed in like this, it's pretty close to a line. You can see it has a very slight amount of curvature. If we wanted to see more of the curve, we could zoom out. Let me increase my x-axis out to a year. That would be 12 months. And once we zoom out to a year, we can see more of the curve. And if, say, I zoomed out to 2 years, it's 24 months, we could see it curving even more. So this is an exponential function with a very small amount of curvature.